All right, we're going to take a little bit to try to understand the concept of phasors. So in class, we've talked about the fact that if I have a cosine type of signal or a sine type of signal, there's two ways of viewing these types of signals. One is to use this identity where I think of cosine of theta as 1/2 e to the j theta plus e to the minus j theta, right? Which is what I've written here. Okay, so I can break my signal up into two exponentials, two complex exponentials, or sometimes the simpler way of writing things is to say that I can view these sinusoidal or cosinusoidal inputs as the real part of a e to the j omega t e to the j phi. All right. So if you think about that to make sense of this, right, you would just have to expand a e to the j omega t e to the j phi, and you guys should know by now that's going to be a cosine omega t plus phi plus j times a sine omega t plus phi. Right? Basically, we use this approach here. We note the fact that typically our inputs to our real systems are these sort of cosine or sine functions, but the math that we do tends to be a heck of a lot easier when we view it as a complex exponential and then take the real part or the imaginary part at the end. Okay? So this concept of phasors, let's focus on that for a second. So if I want to figure out, as an example, let's say I have 4 cosine 1000t plus 30 degrees. Okay, that thing, if I want to figure out the phasors, I can say what's the real part of 4 e to the j 1000t times e to the j 30 degrees. If you expand that, you would see the real part of that expression was exactly that cosine expression. Now I'm going to write that a little bit differently. I'm going to move some things around here. I'm going to write this as 4 e to the j 30 degrees times e to the j 1000 t. This first part here I call the static phasor because it does not move. All right, and this is what in circuits 2 you're going to call the phasor. This whole thing here is called the dynamic phasor, and it rotates as t is greater than 0. All right. So the important thing to note is that as t advances, one thing I can see about this is if I have this angle, this guy can be thought of as 4 cosine of theta, where theta is simply 1000t plus 30 degrees. So as t advances, the angle changes. Okay? So let's kind of plot this thing here. So if I have the dynamic phasor for e to the j 30 degrees times e to the j 1000 t, it has a corresponding static phasor of 4 e to the j 30 degrees. So I would sketch that guy like this. This angle is 30 degrees. The dynamic phasor would sit on top of that guy and then rotate as time advances. Okay, so to try to visualize this, I'm going to try to look at this in a simple little MATLAB script. Okay, So for now, what I've actually tried to draw here is, as a simpler case, I'm going to start out with 4 cosine omega t. Okay, I'm going to get rid of the 30-degree part for a second. Okay, so what I've got on the top and the bottom here, basically what I'm going to draw is, on the bottom I'm showing the real part of my dynamic phasor, and on the top I'm showing both the dynamic phasor as well as the static phasor. Okay, and let's watch how those evolve over time. So I'm going to run my MATLAB script here. Okay, so we'll watch. Okay, so here's my dynamic phasor. So my dynamic phasor is rotating around as the angle changes. What I've also got here is the real part of that dynamic phasor, and I'm also plotting that real part down here. Now notice over here I also have the static phasor, which is not moving. Okay, so let's watch that one more time. All right, so here we go. My static phasor sits here. My dynamic phasor rotates as the angle increases, and the real part is right here on the real axis. That real part is also plotted down here at the bottom. And I can see that that real part basically traces out a cosine as the angle advances. Now, that was for essentially for cosine omega t. Let's say I did it now for 4 cosine omega t plus 30 degrees. Okay, so I'm going to go to my MATLAB script. All right, and I'm going to give this guy a 30-degree offset. Okay, and I'm going to run it again. Now notice my static phasor is now sitting at a 30-degree angle. My dynamic phasor rotates. The real part changes its length as that dynamic phasor rotates. And I can see the evidence of that 30-degree phase shift when I look at the real part down here. Right? If I look at where this guy starts, right? So if I look at this initial value, let's say when the angle is equal to 0, it says that the y-axis value here is 3.464. Well, if I go to MATLAB, what I should have at time t equal to 0 is 4 times exponential j times 1000 times 0, right? Plus 30 degrees. So the way I write 30 degrees is I say 30, and then I have to convert that to radians, so I say times pi over 180, like that. Okay, so I get that result, and I see that the real part of that is 3.4641, exactly what I have right there. Okay, and I could do that at any one of these different angles if I wanted to. Okay, all right. So you should be able to kind of understand this and sort of watch this arrangement to kind of understand exactly what's going on. Now the tricky thing comes in if I try to understand something like this. What happens if I have sine? Okay, a really important thing to remember about the use of the phasor is that the use of the phasor assumes that all my signals have the form of cosine. So if I have a sine input, I have to convert that somehow into a cosine form, which actually isn't too hard to do. The thing I know about a sine omega t is I know that that is the imaginary part of a e to the j phi e to the j omega t. Okay, Or if I expand that out, I know that's the imaginary part of a cosine omega t plus phi plus j times a sine omega t plus phi, like that. So I'm going to do a little bit of a trick here for a second, right? If I were to multiply this thing in here, if I were to multiply that thing by minus j, okay? So let's say I took the, if I took that inside, I'm going to just do it sort of separately like this. I'm going to take this inside piece. Take that inside piece, I'm going to multiply it by minus j. So minus j times e to the j phi, e to the j omega t. That would be minus j times a cosine omega t plus phi plus j times a sine omega t plus phi. Okay? If I go through and carry out that minus j operation, what am I going to get? I'm going to get minus j times a cosine omega t plus phi plus, so minus j times j is 1, so I get a sine omega t plus phi, like that. Okay? All right. So if I look at what I have there, what I can see is that for this expression right here that I just created, what I can say is that the real part of that expression is exactly what I started with, a sine omega t plus phi. So instead of expressing a sine omega t plus phi as the imaginary part of something, I can also say that it is the real part of minus j times a e to the j phi e to the j omega t. Now, if I think about minus j in the complex plane, here's the imaginary part, here's the real part. Minus j points downwards. So minus j is a vector that has a unit length and an angle of minus 90 degrees. Okay, so I can write this guy as the real part of a e to the j phi e to the minus j 90 degrees times e to the j omega t. Or in the end, this guy is a cosine omega t plus phi minus 90 degrees. Okay, so essentially what it's saying is I can take a sine omega t plus phi and express it as a cosine omega t plus phi minus 90 degrees. So this idea that a sine function is essentially a rotation of the cosine function. In other words, basically I take a sine function could be thought as a cosine with a negative 90 degree phase shift. The reason we do that is because we can use real parts all the time instead of having to use the imaginary part, which is kind of desirable when we're analyzing circuits. The whole idea of an imaginary part is usually just kind of annoying to everybody, but it causes us to have to use this sort of phase shift of minus 90 degrees to be able to make that work. So let's say that I had 4 sine 1000t, right? If I were to view that as a phasor, then I would say I have the real part of minus j times 4 e to the j 1000t. Or I can say it's the real part of 4 e to the minus j 90 degrees times e to the j 1000t. Okay, so that means in this case, if I were to do the dynamic and static phasor, here's the real part, here's the imaginary part. In this case, the static phasor points straight down at minus 90 degrees, and the dynamic phasor would rotate from there. So let's real quick look at my MATLAB again. All right, so in my MATLAB, right now what I'm doing is I'm plotting as a function of theta, okay? And let's make my phi 0 degrees, made my amplitude 4, and here's the expression I'm going to do. All right, so 4 times exponential j to the theta plus phi, and what I'm going to do is I'm going to multiply by minus j, and then in my static phasor I'm going to multiply that by minus j as well. And let's watch this guy evolve. So now I can see my static phasor is pointing straight down because of the minus j. My dynamic phasor rotates, and here's the real part. So notice what the real part does. As the angle advances, I see that the real part is tracing out the sine function. If I let it get to the end of the period here, so I can see at time t equal to 0, or basically at the beginning of any period, I see that with my static phasor and dynamic phasor both pointing straight down, there is no real part, right? Which is why I have 0 amplitude. This thing maxes out once I get to a quarter of a period, which is going to be once I'm purely real. So let's watch that one more time. Okay, so here it goes. So my dynamic phasor is rotating. I see the real part getting bigger as he rotates. Now as he rotates up here into the first quadrant, I see the real part getting smaller. Now the real part's going to get bigger and go negative. Now the real part's getting smaller. And eventually I'm back to normal. Okay? All right. So hopefully that helps to understand a little bit more about phasors. You guys should play around with that a little bit so you can see that visualization a little bit more yourself.